we have a sequence of lot of fragments, and these fragments sequence usually it comes in a sequence format called from an Illumina machine. The sequence comes in a sequence format called BCL format. This BCL format will be converted to the most used format called FASTQ format. This is the most used format used for the NGS sequence data analysis, that is the FASTQ format. This FASTQ format is the so this BCL format which is produced from the Illumina machine will be first converted to the FASTQ format. That is the first step involving in the sequence analysis. So usually the FASTQ format, what is the FASTQ format? This picture we will come later. So this is a FASTQ format. It's somewhat similar to the FASTA format which we seen in the GenBank, all these things. But a FASTQ format, the difference is that it says about the quality of the sequence. It has a line which says about the quality of the sequence. How good is the quality? We can see that from this picture. Yes, from this picture, if some of the peaks are overlapping, you can see here overlapping peaks. If overlapping peaks come, we are confused about the identity of that sequence. We don't know what actually the sequence is there about. If there is no overlapping, if only one colored peak is coming, you can see distinct peak is coming, we can confirm that that is A or T or that will be there. But if the peaks are overlapping, the sequence quality will be less. So like that, from the Illumina machine, the BCL format or base calling format will be converted to FASTQ format, and this FASTQ format is the format which contain the quality of that particular sequence. The FASTQ format consists of 4 lines here. 4 lines. It consists of 4 lines. So what these 4 lines indicate, that we will discuss now. So each entry of FASTQ has 4 lines. Okay. A sequence identifier with the information about sequencing run and the cluster. So this is a title the line where it tells about the sequencing run, which cluster it belongs, deals with the sequencing machine and which cluster that the sequence belongs, all these things. Exact contents of this line vary based on the BCL to FASTQ conversion software used. So based on the which software we use for the conversion of BCL to FASTQ, this line may vary. This line mainly tells about the technical details which sequencing about the sequencing run or about the machine and about which cluster it is. So like that, purely technical things are listed in this header line. That is the first line where the sequencing information is present. The second line is the sequence itself. The sequence itself, the base called the sequence ATGC, the sequence itself. Sometimes they denote as N, where we can't confirm a particular nucleotide. The peaks are overlapping, we will just add as N because we are not confirming. The third line, which contain a plus sign, which it indicates that it is sequence ends, sequence line ends. Not sequence will not end. Sequence line ends, or we can say it is a separator. The plus sign is a separator, which is simply a plus sign will be there in the third line. And fourth line is the base called quality score. Usually it is calculated using a software called FRED quality score. FRED plus 33 encoded using ASCII character. It represents the numerical quality score. Usually these quality score were determined by the software called Fred, and is quality score for each nucleotide. The quality score for each nucleotide. The quality score for T is the A, the quality score for T is A, the quality score for this T is A, quality score for G is A. What is this A, G, all these we will tell. So this is how the from the illumina the data comes out as BCL format, and the BCL format will be converted to the most accepted, most used format. From the FASTQ format only every analysis has been done by using different softwares. This FASTQ format is the most widely used format, just like FASTA format for GenBank. It consists of 4 lines. First line will be the identifier line, which consists about the sequencing, what machinery used, the cluster, details about the cluster, details about the run, all these things, technical things. Second line is the original sequence. Third line is a plus sign, which is separator, and fourth line is the quality score, which is indicated as ASCII characters. What is ASCII characters? You can see a different character, less than symbol here. So what is this denotes? You can see. So this score is called Q score. This quality score is called Q score. Okay. What is this quality score? The quality score is given a score of a given base. The quality score of a given base is called Q score. Each base has a score. Okay. Each base has a score. Here the base T score is A. Base T score is A. Base T score is just a number like it. Don't think it is adenine or anything. The quality score of T is E. Like that. These are ASCII characters. So this is calculated by equation. This is Q is equal to minus log 10 E. This E is estimated probability of base call being wrong. So highest quality score indicates a smaller probability of error. If the quality score is high, we can say that the quality score is high, which indicates that the nucleotide is there is no wrong in nucleotide in this position. Okay. When we are adding, the PCR is a technique which a lot of error can occur. Okay. So during this addition of nucleotide, error can occur. If the quality score is high, the error chances of error is less. If the quality score is low, the chances of error in calling that base is chances of error in that of that base in that particular position is high. Okay. So high quality score will be good than low quality score. You can see when you are doing Galaxy, for the analysis of this FASTQ sequence, you can see this type of graph where we can see the quality score here. Quality score usually ranges from 0 to 40. Okay. 0 to 40 is the quality score. Usually a good quality score will be, very good quality score will be 30. If the quality score is 30, is very good quality score. You can see the initial sequences here. That is, these are the sequences. Sequence position. Okay, this is the first position. The initial sequences were of very good quality score. It has a quality score of 36. It has a quality score of 32. It's very good quality score. But when it comes to the last sequence, the error bar you can see at the lower quality area, about 20. 20 is a low quality. You can see. So low quality you can see. So as coming to what 60, 75 base pair, the quality of the that sequence become deteriorating, as we can see from this graph. So as I said, this is the quality score. We need to have a good quality score is around 30 is good. Quality scores start from 0 to 40 and 30 is very good. We can see here the quality score of the initial sequence. This is a sequence from the first nucleotide to 99 nucleotide, and the first sequences were very good quality score, and when it comes to the last nucleotide, the error bar is, we can see it in this region where 20, the quality score is 20, the quality score will be low, so that the sequence at that region is having less quality. Okay. So, high quality score means that sequence at the region, their probability of occurring that or that sequence at that region is very good. So, there is no this is very proper sequence has been sequence is present there. But if it is lower quality score means that sequence, or if it is A is added there. Okay. Actually, we don't have a confidence on A to be there. Maybe it can be T or G or C, because the quality score there is less. So, the graph may be overlapping, and the quality of the sequence at that position is not good. They may also lead to the increased false positive variant called, we would add A there, but actually that position, 95th position, may be T. So, at that area the quality score is less. You can see here there is a symbol, usually symbols indicates a lower quality score. Here the quality score is less, so the symbols are indicated here. So, I will tell what it is, symbol, everything. So, here the quality score is less. So, here the quality score will be lower, so that we do not know it is C, it can be T, we do not know. The peak here is overlapping, and we can't determine. So, it is usually C, the fluorescence of C, but actually we do not have confidence in this region. So, that is the there the quality score is less. So, the sequencing quality reaches Q30, that is the very good quality. Virtually all reads are perfect. So, if the Q30, all reads are perfect, there is no errors in the sequence. And why Q30 is considered as a benchmark quality? This is why Q30, if their sequence quality score falls in Q30, the sequence, all your graph fall above this, your sequence is of a very good quality. So, you can see the quality score, if it is 10 quality score, 10 Q10, 1 in 10 chances of error can occur. When it is 30, 1 in 1000, very good, about 99% accuracy we can see. If it is Q10, about 90% accuracy only. We have 99% for 9 accuracy in the case of 30 Q score. So, from here only we got this A, E, all these things from this table we got. So, you can see different ASCII score and symbol. So, the quality score 0 means at that region this symbol will come. Where is that the less than symbol? Yes, the quality score is here 27 only, that less than symbol. Okay. Here you can see, I will rub that. Here the quality score is only 27. Okay, here 27 only. So, like that we have an ASCII table which shows where is A. A is the quality score of A is of quality score 32, and E is of quality score 36. Very good quality score is been here for most of the sequence. It's a very good FASTQ sequence. All these sequence are being very high quality. So, only one sequence, it is about 27, it's also some acceptable. So, if it is if your sequence is of 0 quality score, the symbol come, that A, if it is 0 quality score, this symbol will come. So, different symbols will come in the fourth line. This fourth line, these symbols can come according to the quality of your sequence. These symbols can come based on the Q score. Okay. I hope you understood. So, we are just going through the basics of whole genome sequence data analysis, and then we will see the methodology, how the sequencing is done for very shortly. We will see how the sequencing is done for ion torrent and solid sequencing by ligation. I think sequencing by ligation is not being used today. So, these two very shortly we will see, and we will wind up. So, actually in the case of sequence data analysis, we are going to do the sequence data analysis using a online tool called Galaxy. Okay. Galaxy is online, and it is available freely online, and you go here and just to take the Galaxy. Galaxy means use Galaxy. That is the, I think I have done it one experiment before my experiment is coming, I think. So, usegalaxy.org is the website. You can go usegalaxy.org, and what you need to do is that you should register here. So, I have already registered as Dr. Noble. You will have a symbol like a register. You can give your email ID, and you can register here first. Okay, register here. This Galaxy is just like NCBI for data analysis. It contains a lot of tools which needed for different sequence analysis. In the case of RNA-seq, in the case of microsatellite, in the case of lot of viral DNA, in the case of small exome sequence DNA data analysis. So, actually every sequence analysis follows somewhat a basic workflow or pipeline in the analysis. So, we have this illumina machine the FASTQ sequence. From the illumina machine we have the FASTQ sequence. Then what we do is that we will use a series of tools from this Galaxy to analyze our FASTQ sequence. What we need to do? We have only the FASTQ sequence of a number of pieces. We have the FASTQ sequence of the fragments which we have made during the sample preparation, fragments made through sonication, nebulization, etc. Now we need to assemble these fragments. For assembling these fragments, we use the help of a reference genome. If we are doing a human genome sequencing, we take a reference genome which is already sequenced from NCBI or genome sequence databases such as UCSC genome browser or somewhere, and using this reference genome we will find out where which piece belongs to. Okay, where which piece belongs to, and then we will finally find out the whole sequence in the proper sequential order. Hope you understood. So, how we will do this? We usually use a reference genome. Based on a reference genome, we have the sequence of millions of fragments which we have produced from the genome. These fragments, where it lies, where it goes, we don't know. So, for that we will take a reference genome. We will take a already sequenced genome, and using a reference genome, is a reference genome of human which is already sequenced. Human genome sequence is available since 2003, I think. So, we have a number of assemblies available in UCSC genome browser. I think last full genome sequence assembly is from 2013. I think we have seen when we are taking that gene sequence for primary designing, 2013. Newer assembly is there. I think it is not fully one. This is the 2013 one we are using. So, using the reference human genome, we will assemble all our fragments and find out after this fragment which fragment will come, after this fragment which fragment will come, after this fragment which fragment will come. So, based on the reference genome, we will assemble all our fragments and make it, stitch it together to form the whole genome. Okay. This is how we do with our sequence. If we do not have a sequence difference genome, we will go for overlapping sequence and find out, we will find out the sequence. That is called de novo assembly, de novo assembly. Okay. Usually de novo assembly, I am not referring that now. So, how using a reference genome, how we will find out the whole genome, that is what I am going to explain to you. So, actually when we get the FASTQ sequence, we have the quality score of each nucleotide. Okay. Then also we will go for the quality score of the whole sequence. So, that process is done by a tool called FASTQ. I think you know that a lot of tools are there in NCBI, BLAST, BLAST, cluster level is not there, and which other tool is present? BLAST, different BLAST, N BLAST, P BLAST, and primer BLAST, and then OR finder, and then many tools are present. Just like that tools, the Galaxy, that server also have several tools. It is not just I have referred 4 or 5 tools, more than lot of tools needed, specially needed for each type of DNA sequence. If it is RNA, there is different tools are there. If it is viral DNA, it is different tools are there. So, I am just telling about the common whole genome or DNA sequence what we are using. So, the FASTQ sequence is there. This FASTQ sequence, its overall quality can be assessed by a tool called FastQC. And then if any region overall quality we just find out, and if any region the quality is so bad, that region we can trim and get the good area. So, that for that we will use a tool called Trimomatic, which is present in the Galaxy. All this actually Galaxy is a we are very used to the we are very used to the graphical user interface. Okay. So, we can't shift it to coding. That is, the people who are very difficult to shift it to coding use this Galaxy. Otherwise, the people who know how to code, they use the softwares which support coding. Actually, the advantage of coding is that actually I will show you, I have just to show what we are doing here using a very small FASTQ file. But actually the FASTQ files are of very big GB size. So, we can't it will take, the Galaxy will take a lot of time for each analysis. We need to take all these tools and analyze our sequence. For that, Galaxy take a lot of time. Days it will take, and a very good system needed. But in the case of command based tools, it is more faster compared to that of the Galaxy. And there also you need a system with a very good memory. So, what we are doing here, we will just take a sample sequence. We will just take a sample sequence. You will get a sample sequence sample FASTQ files you can get from a site called Senado. You can see Senado sample file. You can just search sample FASTQ files. You will get from Senado. I think you can see small files which can be which is easy for analysis and studying. You can get it from here. It's MB files only. If you go Geo website in NCBI, you will get files, but all are very big GB. We can't process properly. So, I have just taken a small file in order to show just what it is happening here. just like a BLAST only, we will upload it and analyze it, that's all. So, so that is what we are going to do. So, what we need to do is that we after entering the Galaxy, we need to register as the user. Okay. Then we need to get the data. For getting the data, we can extract data from the NCBI websites using the particular code, the accession number. You can extract the FASTQ files from the NCBI, EBI websites directly. All these are bigger files. I am not going to take that files. NCBI NRES API. I have not said about NRES. NRES is the search engine used in NCBI, just like Google. UCSC browser, you can just export from there. So, I am going to upload from my computer. I have just downloaded from this Senado. I am going to upload a small file from the computer. Upload file. I am going to upload that. I need to choose local files. I think it is in my downloads. I think it is the FASTQ file. I am just uploading. The status it is showing 0%. Let it upload. Let it upload, and then I will come. If you don't register, the uploading will not be happening. So, the FASTQC file FASTQ file we go for quality check called FASTQC. Then if any portions were not showing the good quality, is being trimmed and removed by Trimomatic tool. And after the trim, you can go for one more FASTQC. FASTQC is a tool which tell about the quality control. You can do it in each step, so that we can see the quality, how the quality increased after Trimomatic. You can go for one more FASTQC. One more time you can do the FASTQC. After the trimming the sequence, you can do one more FASTQC. Then we will go for the genome assembly using a reference genome. Usually in the Galaxy, we use the tool called Spades. Spades are the tool which is used for genome assembly, and genome will be assembled as a reference genome. And after the assembly, and we got the whole sequence, genome sequence, then we can go for finding out mutations in this genome. This is called variant calling. If any SNPs are there, SNP is another tool. If any SNPs or any variations present, different variant calling tools are present in Galaxy. We can find out different mutations present in our genome. Okay, and then after finding out mutation, we can visualize the our genomic sequence using another tool present in Galaxy called JBrowse. So, lot of tools are there. The basic steps follow the same in most of the whole genome sequencing. When it comes to RNA-seq, we will do this FASTQC, Trimomatic, everything, but we will go for annotation of that genes, what genes are present. Some extra tools we will use. That's all difference. Extra tools, you can see the pipelines. A lot of pipelines are available in online. So you can see the pipelines which are commonly used for RNA-seq. So just what they do is that they use different annotations. They will find out the functions of the particular gene, all these things by using different extra tools. So actually, what is the whole genome sequence data analysis is that we will check the quality of the sequence, and the main thing is that we will assemble the sequence using either reference genome, here the Spades is using reference genome, or by de novo by using overlapping sequence. So in both ways we assemble the sequence. This is the most important thing in the DNA sequence analysis. And then we will find out variant, and variant calling we will do, and finally the data visualization we will do. And different tools can be used. CSC genome viewer is there. Different tools can be used for the genome data visualization. In Galaxy we use JBrowse. So that is all about the genome sequencing. and data analysis. These are the common steps we use in data analysis. This we will follow in every software. So that's all. So I think this is still 0%. Done? No, start. Oh, sorry, I have need to give start. Sorry. So I have done, and you can see my then close. Here these regions we can see the tools, and here these regions you can see the history what I have done, and here these regions you can see the results which we get. So we have uploaded that sequence here, and then we will just go through the FastQC just to show what is happening here. You can just type what tool, spades or what tool you require. You just type the tool, just upload that thing in the tool, that's all. So FastQC, this is a tool, just select it. So our sequence is already uploaded there. Make other things as adapter list, contamination list all as default, and just do the FastQC, and you will see the quality of that FastQ file which we have uploaded. So that is what we are doing in the Galaxy, and this is what our whole genome workflow is about. This is what we are doing in a very old genome sequencing data analysis. People do with different tools, and people do with mostly with the command line based tools, so that it will be more faster compared to that of the Galaxy tool. You don't need to worry, you can use Galaxy tool. It will take a bit time only. You can use Galaxy, and you can just get your FastQC, and it is already added to the queue, and it will take bit time. We can continue with our